Okay. Anyhow, impurities. Oh yeah, sorry. So lots of schools use sulfur, but in this case we're using copper sulfate. Sulfur is actually really easy to use because it's easy to melt and so forth. But anyway, impurities can be removed from a solid, soluble substance by knowing the solubility. This word solubility means ability to dissolve in water of a solid. Solubility is most commonly given as something like this: 53 grams out of 100 grams of water. Something like that. So that means 53 grams of copper sulfate can be dissolved in 100 grams of water. By the way, I just wrote this. This is not exactly accurate or anything. I'm just showing you that solubility is commonly written in this form. For example, a sample of impure copper sulfate can be purified using crystallization. And explaining crystallization requires an example. So what we have here, excuse me, I'm going to just okay. Sorry, I've got a cold. A. Imagine you have 50 grams of an impure sample of copper sulfate. So my impurities are dotted like this. So all the diagrams that are in this book are actually drawn scientifically. Like the beaker, it's a very simple looking line thing and so forth, and all the arrows are pointing towards whatever. Everything's labeled as well. Okay, so you've got a beaker, you've got impurities, which are the little black dots, 50 grams of impure copper sulfate crystals. Then B, first dissolve the sample of impure copper sulfate in a 250 ml beaker with minimal water. Okay, I'll explain why we use minimal water later. But here, copper sulfate is called a solute because it dissolves into a liquid, and that's the definition of a solute. The liquid is labeled the solvent. The solvent is the liquid that does the dissolving, so as it is the substance that dissolves the solute. So if you have an example like salt and water, salt will dissolve in water, so the solute would be the salt and water would be the solvent. Okay, just these terms you need to know. If we reach a point at a certain temperature where no more solute dissolves, then we can describe such a solution as a saturated solution at that temperature. Saturated. So, I mean, imagine a cup of water, cold water and sugar, and you just dump in like a tablespoon of sugar. And no matter how many times you mix it, it'll still have some sugar left at the bottom of the beaker or the cup, right? That means the solution here, okay, is saturated. That means at that temperature, which might be room temperature, if no more solute dissolves, the solution is saturated and some of the crystals will remain undissolved. So basically this solution here is saturated now. Okay, so I'm going to label this as saturated. And some of the copper sulfate with the impurities have not dissolved, some have dissolved. Remember, we used minimal water, and I'll explain why in a moment. Okay, we want to use the least amount of water as possible, okay, but that doesn't mean that you're going to use a tiny little bit. We're going to use some, just to a certain extent. So what we have is undissolved copper sulfate with the impurities, and we have some of the copper sulfate in solution with the impurities. So now this brings us to this thing called a solubility curve. Now, every ionic, actually, I'm not going to use that word, every compound has a solubility curve. And what that is temperature is on the horizontal axis, and the mass of the solute or the solid is on the vertical axis. And look over here, the units, grams per 100 grams of water. So this is the mass of copper sulfate that is dissolved at certain temperatures. And you can see the higher the temperature, the more solute will dissolve. That's common sense. It's logic, right? I mean, if you get a cup of hot water and you dissolve like a whole tablespoon of sugar, more of the sugar will dissolve than if I did that with cold water, right? Okay, so basically this is just, logic, and usually the solubility curves, they all look like this, okay? So this is an example of a solubility curve. It is a graph that depicts how much of a solute can be dissolved in 100 grams of water at various temperatures. As you can see, it's 100 grams of water. By the way, on a side note, 1 gram of water is equal to 1 ml of water. Remember that? So here we are. Most times we do not require a solubility curve for crystallization, but it's included here for you to understand why heating a solution with undissolved crystals will help dissolve crystals at higher temperatures. Okay, so basically what we're going to do is take this solution and we're going to heat it up so that this extra little bit dissolves in this minimal water, okay? But obviously at a higher temperature. So let's go back. Okay. So from the solubility curve, we can see that approximately 53.2 grams of copper sulfate will dissolve in 100 grams of water at around 50 degrees Celsius. So going back to this graph, 52 degrees Celsius, we go up and then we look to the side. Obviously if you use a ruler it'll be a lot better, but apparently over here is around about 53.2 grams of copper sulfate. And this is why we need to heat the solution in order for all of the copper sulfate to dissolve. Remember, how many grams of copper sulfate did we have here initially? We had 50 grams of impure copper sulfate crystals, and at 50 degrees they tell us in the graph that 53.2 grams of copper sulfate will dissolve. So that means all of it will dissolve like this, okay? We heat the beaker in order to dissolve the remaining undissolved copper sulfate crystals. Heating a solution to dissolve a solid creates a supersaturated solution, which is a solution that has dissolved more solute substance to be dissolved than when it was originally saturated. So originally it was saturated, okay? But now that we've heated it up and we have dissolved more copper sulfate, it is supersaturated. That's what it means. Okay, so then after that, oh, by the way, looking at the diagram again, we've got the tripod, we've got a gauze mat, we've got the Bunsen burner, and note, we've got the open hole. The open hole allows more oxygen to go into the Bunsen burner and it'll give it more heat, and that will allow for this flame to be very hot. And so it just says here, heating the solution will help dissolve the copper sulfate crystals for a supersaturated solution. And I'm not going to explain that yet until I talk about it. Here, D, continue to heat the solution until the volume of the solution is reduced to approximately half, or more if possible. Reducing the volume encourages crystallization, okay, as shown in the image. But what I want to talk about is, as we go back, okay, so what we have done here, we're heating the solution. We're heating it such that the water is actually vaporizing out, okay? It's coming out and it's creating a supersaturated solution as well, and it's extremely hot. So the more heat that we apply, the hotter it becomes. And basically what is happening is that it's getting hotter and hotter and hotter and hotter. More of the copper sulfate can dissolve, but this also means that we can reduce the volume of the solution. So what we've done is we've reduced it to approximately half, okay, like so. Now there's a reason why we reduced volume. It's because what we do is we remove the beaker from the heat and we cool it. So at boiling temperatures, this is what it looks like. Everything is dissolved. When cooled to room temperature, and we further cool the solution in an ice bath, what happens is the copper sulfate starts to crystallize out, okay? And that's because at that volume of water and at that temperature, not all the copper sulfate will dissolve, as we know from our solubility graph, okay? So as it gets cooler, less copper sulfate will dissolve, won't it? Right? And so if I get even cooler, it'll be only about right about what, 25, I don't know, grams or so will dissolve. So here what we have is we go from, 100 to 25 to 0 degrees Celsius. This is I'm going to be careful, by the way, because we don't want this to freeze. But the point is, as it gets cooler, the more copper sulfate will crystallize out. But what do you notice? The crystals are clean. They have left the impurities in the solution. Because what happens is, when they crystallize out, they're like, oh, only copper sulfate people. Not people. Copper sulfate crystals come together now, and all the impurities, you guys stay out in the solution. And that's what it's done. It's discriminated, pretty much. So you'll notice that the copper sulfate has started to crystallize out. Remember, when the crystals reform, they leave any impurities in the remaining solution. So what have we done? We have taken impure copper sulfate crystals and we have created pure copper sulfate crystals. And then we filter the solution and rinse the crystals in minimal water, and of course some copper sulfate will be lost in the remaining solution, okay? We're losing some substance, okay? But at least we have what we wanted, pure copper sulfate crystals. But the filter crystals are pure copper sulfate crystals. Now note, the crystallization here was demonstrated in a beaker, and you'll do that. But in many cases, crystallization is done on an evaporating dish or crucible, and this is because water evaporates faster than from an evaporating dish or crucible than a beaker. So it depends on your teacher, depends on your school, whether you'll be using a beaker or a evaporating dish or crucible. Now what you have is, this was set for homework. Okay, I'm going to tick that. You guys can check the answers on Edmodo. The answers should be there. So try it out first and then check and mark and then ask any questions that you might have. Okay, so that's the end of crystallization.